Alright, this video is going to cover probabilistic reasoning in the social sciences, and this comes from chapter 10 of Keith Stanovich's book, How to Think Straight About Psychology. Probabilistic reasoning comes from the 1935 book by Karl Popper titled, I think, The Logic of Scientific Investigation. And it has to do with how to interpret probabilistic events. And so in physics, for example, we can say with confidence what will happen. We can predict with confidence what will happen if we know the material properties of two objects, what will happen when they smash into each other. We know how much of each object will be exchanged. We know how much force will be exchanged and what the result of that impact will be. And if it didn't happen the way that physics predicts, then we would have to revise our understanding of physical properties of objects. Now, in the social sciences, we generally cannot make predictions like that. What we can say is there's a certain probability that something will happen. And so we can predict with confidence that the probability is that such and such will take place. And while that weakens the strength of predictions, if we understand what those probabilities are and we understand what they mean and how to interpret them, we're getting as close as possible to the kinds of predictions we see in chemistry and physics. And so that process is called probabilistic reasoning. So I gave this example in class, and almost none of my students knew how to play poker, what the rules of poker were. So I give the example of this poker hand that's very rare. It's when you have, let's say in a game of 5-card draw, all five of your cards belong to a sequence, and so it's like 2, 3, 4, 5, 6, or I give the example 4, 5, 6, 7, 8, and so all the numbers are in a row. There's no gap in there, so this is called a straight. And if all of those cards are the same suit, like they're all hearts or they're all spades, then that makes it a flush as well, so it's a straight flush. And have both of those things is extremely rare. The probability of winning goes up astronomically. I think there's like a 0.0001% chance that someone will have a stronger hand than you if you're holding a straight flush. So that probability is really good. And so you should bet as much money as you have to bet, or if you're trying to like trick them, just kind of lure them in, maybe act like you don't have a big hand or whatever. I don't play poker. I don't know how to beat other people. The point here is that a straight flush is likely the winner, but it's not always going to be the winner. And so there's a probabilistic certainty, not a complete certainty, but a probabilistic certainty, a high probabilistic certainty that you'll be the winner. To give an example that I'm sure you're all more familiar with, we can say that men are, on average, across the entire world, taller than women. And so the average height of man is taller than the average height of women. But that doesn't mean that any man chosen at random will be taller than any woman chosen at random. It just means that the probability is good that the man will be taller than the woman. And I've got some examples of that on this probability curve, and so I'll return to the probability with height. Again, most social scientists don't use height and gender as like the key foci of their research, but I just want to give a really simple example. A more complex example might be the relationship between regular THC consumption and the increased likelihood of mood disorders when the THC consumption happens in young adulthood. So there's a strong indication that there's like this twofold increase in anxiety diagnoses and severity. So in participants, in young adults who are regular consumers of THC products, the likelihood of anxiety goes up twofold compared to peers who are not regular consumers. That doesn't mean that if you are a regular consumer, you will have anxiety. It just means that the likelihood goes up. We can also say the same about smoking cigarettes. We know that there's a relationship between cigarette smoking and lung cancer and cardiac disease and a whole bunch of other health problems. But that doesn't mean that if you smoke one cigarette, you're going to get lung cancer. Or even if you smoke cigarettes for 40 years, you're going to get lung cancer. Kurt Vonnegut, the American author, famously wrote, like when he was in his 70s, I'm going to sue the producer of Pall Mall cigarettes, which I've been chain smoking since I was 15. They promised me that I was going to die, and here I am, still living. So he didn't die of lung cancer, I don't think. He lived to be quite old. Um, so it doesn't mean that if you're a chain smoker, you will get lung cancer. But that doesn't mean that if you are one of the minority who do not get lung cancer, that no one will get lung cancer. So again, we're talking about probabilities here, not certainties. But that doesn't mean that um, those predictions are somehow weaker. They're as good as we can do. And if we accept that, then we can really understand the breadth of what social scientists are capable of. We'll see that a little bit more in chapter 11. So this is a probability curve, and this series of lectures has been about applying scientific reasoning to the social sciences, and we haven't talked about the random curve in statistics yet, but it's been at play in everything we've discussed. So whenever a prediction is made, such as men are taller than women, or regular users of THC products will likely develop a mood disorder, anxiety, or depression, or have an increased likelihood. We're just talking about probability of these things happening. And so this is a normal distribution, and this is an assumption when you use statistics. And so when we're talking about probability, there is a 2.35 probability that a group of people on any distribution, whether it's THC users and development of mood disorders, or cigarette smokers and the and cancer diagnosis, or height of men and women, 2.35% of the distribution of the people will be highly likely. So maybe if it's smoking THC products, 2.35% are going to have severe anxiety. 2.35% are going to have almost no anxiety. The majority, however, will have an increase in anxiety. So down here we'll have like minimal anxiety and then no anxiety. Then up here it'll be like super high anxiety, clinical, like you need to take a tranquilizer kind of anxiety. And so that's kind of at play with all these predictions. We can say with a strong confidence that this is going to be true. So like 68%, there's a 68% chance that I'll be accurate with that prediction, and then a very small probability that it'll be much worse than I expected, and a small probability that it'll be better than I expected. And so that's always at play. And so let's give an example here in comparing height of men and women. So I've got two distributions. I just yanked these from Google. We've got this. This is a distribution of 100 men, American men, and their height. And this is a larger distribution. There's no given number here, but I think it's like on the magnitude of hundreds of thousands of women who submitted their height. So the average height of a woman is 5'5". Average height of a man is 5'7". So there's a 2-inch difference. That's not a huge overlap, and I put them together on the same graph here. Again, I yanked this one from Google as well. This has the average height of man at 5'9" to 5'10", so it looks like I landed right there in the average, personally. And for women, 5'3.5", so pretty close to the previous graphs. But notice all this overlap here. So this, anywhere in here, is an example of a man who's shorter than the woman here. And we've got about a third of the distribution on both sides, maybe just under the third, a quarter of each distribution. And so for any two drawn at random, there's probably going to be about a 25 to 30% chance that the man is going to be shorter than the woman. But the great majority of people on this distribution, if we were to pick a man and a woman, we're going to find that the man is taller than the woman. But that doesn't mean I can predict with 100% accuracy that the next man that I meet will be taller than the next woman that I meet. But there's a 75-ish% chance that that will be the case. So again, the predictions we make in social sciences are never as 100% accurate as we see in like physics and chemistry, but that doesn't mean that we can't make predictions and we can't make recommendations based on those predictions. It just happens to be as far as we can go. We can't go further than that in the social sciences. So I talked about smoking and lung cancer. We all know someone who smoked a lot and then didn't get cancer, and we say, well, I guess I'm going to smoke then. My dad refused to wear a seatbelt his whole life because when he was first driving, he was like racing and got in a car accident, wasn't wearing a seatbelt, and he was thrown from the car. And the car was completely totaled. If he had been harnessed in, then the steering column would have crushed him, just the way the cars were built back then. So there was objective evidence that he survived because he was not wearing a seatbelt. So he said, therefore, I'll never wear seatbelts. If we look at the probability curves, let's go back over here. We can say that he happened to be like right here, maybe on that probability curve. He was the 2.35% who would have died had they been wearing their seatbelt, but the great majority would be better off wearing a seatbelt, and even in extreme cases. But he was down here in the minority, and so he never wore a seatbelt. But each time, that didn't mean he was going to survive. It meant that he had a 2.35% chance of surviving a similar serious accident. So he wasn't applying the actuarial tables, which are the statistical prediction charts that help us make those sorts of decisions. The reason why seatbelts are required by law now in all states is because the likelihood of surviving with your seatbelt on is so much higher than surviving a car accident without a seatbelt. Same thing with like helmets and riding a motorcycle, although some states allow that. All right, this question is going to demonstrate how to make probabilistic decisions and the importance of understanding variance given the size of a sample. Now, this was pretty complicated. My students struggled with it, so I'm going to try to take it slowly. Imagine that a town is served by 2 hospitals. This comes from the Stanovich book. In the larger hospital, 45 babies are born every day. In the smaller hospital, 15 are born every day. As you know, about 50% of the babies are boys. We'll just assume that sex is black and white and that it's evenly distributed between males and females. Sometimes there are more boys than girls, sometimes more girls than boys, of course, but over the year, it's going to be about a 50-50% average either way. So imagine that for a period of 1 year, each hospital recorded the days on which there were more than 60% of the babies were boys. So more than 60% of the babies born on that day were boys. Which hospital do you think recorded more such days? Now, when I first read this, I thought, well, it's 50-50, so it doesn't matter how big or small the hospital is. Half of the babies will be boys, half will be girls. But the trick is that on any given day, that probability may not hold. It's the most likely outcome. But look, 45 and 15 are the 2 numbers, which means that it's never perfectly 50-50 because you can't have a baby who's born evenly between both. So it's going to be more boys than girls, and it can never be an even number if it's an odd number. So maybe 51%, 49%, or 52%, 48%, so pretty close to 50, but not perfectly. Now, over an entire year, because of random chance, some of those days are going to have more boys and some of those days are going to have more girls. And remember, if we look at this normal distribution, if 2.5% or about 2.5% are like extremely rare occurrences, but they do happen, we might say this is like 70% are boys, and over here 70% are girls, and here 60% are boys, and here 60% are girls, and then here it's like pretty close to 50-50. So the most days are going to be close to 50-50, but occasionally over a 365-day year, 2% is like 6 to 8 days are a lot of boys, and then the same, a lot of girls. And so which hospital is more likely to have that? And the answer is the smaller hospital, because 15 is such a smaller number than 45 that the spread is going to be significantly higher on those rare occurrence days, because there won't be as many other babies being born to level it out or even it out to get closer to the 50% expectation. To give a more extreme example, imagine that it was a tiny hospital and there was like maybe one person working there, and they have like one baby a day. That means every day, 100% of the babies will either be male or female. You can't have even any closer to 50% than that. And so, on any given year, you would expect 180 of those days to record 100% males. And that would be an absurd number, but it has to work out that way, or pretty close to 180%, 180 males, or days with 100% males. So as you get bigger with that sample, 15, you're probably not going to have any days. Maybe one day where 100% are all boys or 100% are all girls. But like 45, it's getting pretty rare for 100% of the babies born that day to be all boys. So the larger the sample, the lower the variance across that sample. So the closer you're going to get to that normal distribution. If you picked one person at random, they might be like over here. There's a probability that they'll be right here, and that would not represent the distribution. And if you couldn't tell, I was pointing at the 2.35%, which is 2 plus standard deviations above the mean. But the bigger the sample, the more likely you're going to get a normal distribution. The smaller the sample, the less likely you'll get a normal distribution. The smaller the sample, the greater the variance. The larger the sample, the lesser the decrease of variance. All right, so let's look at a question based on that. This was a problem that I think ChatGPT wrote for me, or I might have changed it a little bit. And I wanted to give like a sociological question or a semi-sociological question. So imagine that a study found that 3,000... Oh, wait a minute. No, this came from Stanovich, sorry. A study found that 3,141 counties in the U.S. A study of 3,000 plus counties in the U.S. found that the counties in which the incidence of kidney cancer was lowest tended to be rural counties that were sparsely populated. And so, kidney cancer was the lowest in sparsely populated rural counties. So you might think, okay, sparsely populated, you're not interacting with that many people, it's rural, you're outside, there's a lot of space, not as many pollutants. Maybe like cleaner health or cleaner eating because you're eating agricultural products and so on. You can kind of make up an explanation for it. But the same study found that kidney cancer was the highest in counties that were rural and sparsely populated. So wait a minute. All those things I just used to defend why the majority of counties with no or low incidence of kidney cancer were irrelevant, because the same is true for high kidney cancer incidence. How is it possible for both of these to be true? And the answer is variance. The smaller the county, the fewer the number of people, which means the less reliable the probability curve. You're more likely to get people on the outliers if you have a very small population. So the outliers appeared on both sides, that the counties with the most kidney cancer were rural and sparsely populated. The counties with the least kidney cancer were rural, sparsely populated. So finding that, there's a confound, and the confound is sample size. The smaller samples tended to yield less reliable results. I'll give one of these questions, so we'll do the second one here, and then I'll wrap it up, because I feel like if I'm getting tired, you're probably also getting tired with all these examples. So the gambler's fallacy is the inability to apply probabilistic reasoning to making decisions that are making gambling decisions. And so gamblers tend to be dumb because they're not applying simple principles of probability to their decision making. In a casino, for example, the game with the highest, when you're playing the house, the game with the highest probability of winning is roulette when you pick a color. And so you can pick red or black, I believe. And there's a 49% chance that red will win, a 49% chance that black will win. So you have a 49% chance of winning on either side. Is that right? Yeah, 49 equals a 98% chance across those two. And then a 2% chance just goes to the house. So that means there's always a 1% chance that you'll be, or a 2% chance that you'll be wrong. Excuse me, a 52% chance that you'll be wrong no matter which color you pick. But still, 48% chance is as good as you get. So if you try enough times, the probability curve will show that you win 48% of the time and the house wins 52% of the time. So that's like the best odds you get, which are still in favor of the house. Anyway, imagine that a slot machine boasts a winner on average of once out of every 50 pulls. So they can be programmed this way, that this would be a 2% chance that any given pull will be a winner. Now imagine that you are watching as your friend Jackie puts in the money, pulls 49 times, and everyone was a dud. She's like, I don't have any money left. And you think, there was 49 duds. I bet the next one's going to be a winner. What's the probability that the same machine will yield a winner the next pull? If you're applying the gambler's fallacy, you'll think, well, what are the odds of 50 duds in a row? Well, the odds of 50 duds in a row would be actually pretty good, but the likelihood of the next pull being a winner is still going to be 2%. So over an entire day, the odds, the distribution is that the odds will be one winner for every 50 pulls, but that doesn't mean that every 50 pulls has a winner. So there's still a probability curve. There's still a chance that 50 pulls in a row or 100 pulls in a row will not yield a winner. That just means they'd have to be balanced out by 50 pulls with 2 winners or 100 pulls with 4 winners, and so on. All right, so there's the explanation, and I actually did some of the math there, which you can pause and look at, but I think, yeah, I'm done with those, and I'm done giving you examples, so hopefully that wraps it up. Chapter 11 is going to look a little bit more in the social sciences, how this plays out in ways that we often fail to apply probabilistic reasoning.